بسم الله الرحمن الرحيم والصلاة والسلام على سيد المرسلين سيدنا محمد وعلى آله وصحبه أجمعين. نبدأ إن شاء الله في السيشن في موضوع Catalysis seminar rooms إن شاء الله. We have invited speaker from Spain, Professor Hermenegildo Garcia.
Yes, very complicated.
That's all right. Professor Garcia performed his research work in teaching at the Department of Chemistry at the Polytechnic University of Valencia and Institute of Chemical Technology. He is the principal investigator of the research group multidisciplinary with over 15 members, and their research interested including organic photochemistry inside zeolite and the use of zeolite as heterogeneous catalyst in organic reactions, preparing electroactive systems, or encapsulates within zeolite, and the use in preparing of solar cells. He has published above 180 research papers between 2010 and 2014. And he has about 500, 700 publications during his career. And he has published in Natural Materials, Natural Photo, Calls, Natural Communication, Chemical Review, he has 8, and other journals, international high impact journals, most of his research. During the last 5 years, they have been cited more than 12,000 times in research papers. The H factor for Professor Hermenegildo Garcia is 74, with an average of citation per year per papers of 38, and appears in the world's most cited chemists list over last years, according to the ISI database, as well as in the list of the most cited research in the area. Welcome, Professor Garcia. And his talk will be about...
It's written there.
Is it written? Okay.
Thank you very much for your kind introduction. Yes, I have mine. I would like to thank also Professor Asiri for organizing this meeting. And actually, we have heard this morning a very nice talk about nanotechnology. And this is a continuation of the talk, because we are going to talk about nanotechnology, graphene, because graphene represents just the limit of the thickness of a material, but applied to a different thing, not to cure cancer. Although here we have an image in where we have a cell, and inside the cell we have the green color, and the green color are particles of carbon instead of metals. One of our research lines is just to find replacement for metals, and in this case I will comment about the use of graphene as catalyst. So then in my talk I will shortly comment about the importance of carbocatalysis, and then I will comment on how we prepare graphenes. Our uniqueness is the way we can prepare different types of graphenes, including also doped graphenes, and I will just go on in the use of graphene as catalyst for oxidation and for hydrogenation reactions, and then I will complete with some conclusions. So in industry, most of the processes are currently carried out by using a catalyst. And when you consider the catalysts that are nowadays used in industry, you find platinum, iridium, rhodium, mainly for petrochemical processes that are carried out in very large scale. So they are noble metals, and also other type of metals that are not so costly, but also they are classified as critical metals. And in Europe, there is a call trying to find replacement for these critical metals, because really there are only a few mines in the world. So the amount of tantalum, rhenium that we have is really limited. And actually, there are many, many types of reactions. But when you consider what are the mechanisms of these reactions in reality, there are not so many different types of mechanisms. The mechanism, one of the mechanisms, general mechanism, is that metals can act as Lewis acid or basic centers, and also metals can act as oxidation and reduction processes. So the point is, can we introduce in graphene the same type of sites? It's possible to use just a carbon that can have also redox sites, or carbon that contains Lewis acid or basic sites. And I will, as the talk go on, I will show you that it's possible to introduce this type of sites in just carbon in graphene, so therefore we can replace metals for many different reactions. So what is carbocatalysis? Carbocatalysis is to develop catalysts that are based almost exclusively on carbon. And particularly graphene is one atom thick bidimensional layer of sp2 carbons, so really it represents the limit in the thickness of a material, because we have a thickness of only one carbon atom. And graphene has many different advantages. One of them is that when it's prepared from biomass, because graphene is made of carbon, so then it's sustainable, so it's a renewable material, and it's affordable because carbon is a cheap element, and I will show you how we prepare, so it's easy to prepare and has limited toxicity. So we have made toxicity in different types of cells, and you have to use very high concentrations to start noting some effect. And also graphene allows us to introduce some active sites that can be used in catalysis. So when we compare all these things, for instance, with the price of gold, where 1 ounce has a cost over $1,000, so this means that the kilogram is $30,000, the kilogram of gold, so the replacement of this as catalyst for carbon has many, many advantages. So how can we introduce active sites on graphene? So this represents a single layer of carbon, and what happens is that when you have ideal graphene, there are no sites, but most of the graphenes that we are preparing have some defects, and defects are really the active sites. For instance, the periphery can be like this, armchair, or the periphery can be in that way, zigzag edges, and the periphery always have catalytic activity. Why? Because it happens that this carbon is not fully saturated, so has unsaturated coordination. For instance, can be dangling bonds or can be radicals, so these are really active sites. But also, other active sites are oxygenated functions. For instance, I will comment that quinones and hydroquinones are really very good redox pairs in graphene. And also we can introduce some other heteroatoms, for instance boron or nitrogen, and so in that way we can introduce acidity on graphene, and also we can introduce basicity on graphene. So basically the point is that the effects on graphene is possible to engineer a graphene that contains the effect that can act as a catalyst in organic reactions. So let me show how we prepare graphene. So we start with some biopolymers. Typically they are polysaccharides, for instance alginate or chitosan, and they come from biomass. So here it represents what is the origin of these biopolymers. So they are renewable materials, and then what we do is we pyrolyze these biopolymers, and then we obtain some carbon. This was already known long time ago. So this carbon has a name they call turbostratic, static because there are some layers are stratus in Greek, so they are turbostratic carbons, and turbo means that the layers, they are not well packed. And also these carbons, they are called graphitic because they tend to be like graphite, but it's not really still graphite. So we pyrolyze these precursors, these polysaccharides. We have this carbon here, you can see that the size is very large, and then the interest is that in contrast to graphite, in where exfoliation is not possible, what happens is because this carbon is really special, is really different, so then by sonication we can exfoliate and we can obtain graphene in suspension in a liquid phase. So here are different magnifications of the carbon that we are preparing. So this is the carbon, and the carbon here has a name, turbostratic carbon. Turbostratic is that because we have layers, and if we expand this image, what we see here is really that we are forming some layers that at the end will be graphite. For instance, here one layer, another layer. When you consider just the external surface, is clearly something that is flat. So we have this that is made with layers, and then we sonicate and we obtain this, that is the typically appearance of graphene. What you have to notice is that this is the scale, 300 micrometers, and typically graphene is about 1 micrometer. So this layer is really a very long graphene layer. What we are talking is about just a small piece of this expansion. So this is the graphene, and we can even magnify it more and have high resolution electron microscopy. And when you have high resolution, you can really see the order of the atoms in the material. So at different length scales, this is the carbon that we are producing. And the conclusion of this is that we can prepare in a very easy way, starting from precursors that have no price, very cheap, some graphene. Besides electron microscopy, we have to do also spectroscopy, and this is the typical signature of a graphene with the 2D band. This 2D band is usually used to know how many layers we have. If this 2D band is very sharp, so then we have single layer graphene. If it is a little bit broader, so then we have few layers or multi-layer graphene. And this is the graphitic band, and then we have another band here that is related to defects, to sp3 carbons. So we have a graphene that contains some defects, but as I have commented earlier, we need the defects if we want to have some catalyst. We have some defects, and also we have a few layers of graphene. This is very interesting. This is the X-ray diffraction of the carbons when it's a powder, and compare with the XRD of the graphite. So the XRD of the graphite has very sharp lines, so this means that graphite is highly crystalline, and for this reason, when you try to exfoliate or you try to sonicate graphite, it's not possible. The yield of exfoliation is very low. However, the XRD of our material, of our carbon, is very similar to the graphite, except that the bands are very broad. So this means that the crystallization of our carbon is very poor, so we have something that is very poorly crystallized, and for this reason we call graphitic. So it's not really a graphite, it's graphitic. And also it's important to notice that there is a shift in this peak from here 25 to here 23 degrees. This shift means that now the layers are more separated. So here the separation between the layers is 0.34 nanometers, and for this reason it's very difficult to exfoliate because the interaction between the layers is very, very strong. But this shift means that now the separation in the layers is 0.5, 0.6 nanometers. So this means that they are further separated, so now it's much easier to exfoliate. So for instance, here the yield of exfoliation is almost complete in some of the materials. So this means that if we have 1 gram of this carbon residue and we sonicate, we have 1 gram of graphene. So the yield of this is very high, and this contrasts with the difficulty of graphite exfoliation. And the XRD clearly provides a nice example of why. What is the reason for this? Of course, always that you want to prove that you can prepare single layer graphene, you have to do AFM. And in AFM, this is the image, the frontal image of the material. And here we have a line, a white line. This allows us to measure what is the difference in height between this point and this point. And in A, in the plot A, the difference in height is 0.4 nanometer. 0.4 nanometer is just the size that is expected for a graphene. So in this case, what we have is single layer graphene, but we can prepare also few layers graphene. For instance, this case B, in where even in the image, in the frontal image, you can see that there are some layers here, some terraces, but measuring the height, the difference in height between here, this point, and this point, you observe that this 4 nanometers. 4 nanometers is about 10 layers of graphene. Of course, here, because we have 4 nanometers, the noise of the measurement is much lower. Always that you go to the limit of the technique, because we have only 1 atom thick layer, so then the noise is much higher, but this is normal. And also we can prepare a few layers graphene, for instance, in this case that we have about 4 layers of graphene. And the typical size of the graphene that we can prepare is about 1 or 2 microns, so this is very normal and very common. Besides graphene as powder, and then we sonicate and we have dispersion of graphene in a liquid solution, we can also prepare films on certain supports, on substrates. So here there is a frontal image of a film of the precursor. You can see here that we have a spot, and this spot is on purpose to show that the precursor forms a very nice film covering the substrate. Actually, these precursors, they are called filmogenic. Filmogenic means that they form very nice films, and modern nature has used these materials just to form the skin of insects and the skin of molluscs and crustaceans. So this is the precursor. This is another image of the precursor, and when we heat and we pyrolyze, sorry for this, then we obtain the graphene. So this is the biopolymer, and here we have the graphene with the logo of our university. And if you have single layer graphene, you don't see anything at all. It seems that there is nothing. So here what we have is 4 layers graphene, and with 4 layers graphene you start to see some gray tint, gray color on top of this. And then we can scratch this graphene and go to electron microscopy, and then we observe here the formation, the presence of the graphene. So this is the process that we follow to prepare the films. The process starts with a substrate, typically quartz, but also can be used some glass. And the glass has to be clean, and then we deposit by spin coating the precursor, the biopolymer. This precursor is annealed. Annealing means to put under humidity for a long time, a certain temperature. So we think that the annealing allows the ordering of the chains, and then we pyrolyze, and then we have the graphene. These are the images of the precursors. Look how nice are the films, because these precursors, they are called filmogenic, so they are polysaccharides, but not all the polysaccharides can do this. Only a few polysaccharides can do this type of films, and these polysaccharides, they are the filmogenic. In this particular case, we have chitosan, and these are the concentrations that we are using. So 200 milligrams of chitosan dissolved in this solution of water. Another thing is that we are using green solvents, so water is a good solvent for all these things. And this is the layer. And this layer has 50 nanometer thickness, so we make a cut on the thing, and allows us to measure what is the thickness of the layer. And when we pyrolyze, then the film becomes rank. So we concentrate a lot. And this is because the structure of these biopolymers changes completely, and now what we have is a flat graphene. And then from 50 nanometers, we have graphenes with 10 layers. But we can prepare more diluted. And if we prepare more diluted, then we have here a thickness of 23 nanometers, comparing this high and this high, 23 nanometers. This is the image. Again, very nice, very smooth surface. And when we pyrolyze with this thickness, what we have is 4 layers graphene. So we can control pretty well what is the thickness of the precursor, and by controlling the thickness at the end, we control how many layers of graphene we form. For instance, in this case, with 4.7 nanometers of the precursor, at the end what we have is single layer graphene. So in a film, one characteristic of the graphene is that graphene is very transparent. So this scale is transmittance of light, and this is 100. Have a look to this, because 1 layer graphene has a transparency of 99%. So all the light goes through, so the eye cannot see anything. But as soon as you have 2 layers, because there is pi-pi interaction between the layers, so then the eyes start to see something, and it's because the light is not totally transmitted. So now we have about 95 transmittance in the whole range of UV and visible wavelength. And if the number of layers increases, for instance 4 layers graphene, so then already the naked eye can see that there is something, that there is gray. And there is gray. Also Raman spectroscopy. This is the Raman of a single layer graphene. Of course, the Raman signal is very weak. It's very weak because we have a single layer of atoms, but if we have 2 layers or 4 layers, so then the signal of the Raman increases in intensity. XPS is very important in this area, because when you have good graphene, you have only a single peak of carbon in XPS. And here we have 2 peaks. One peak is the carbon on graphene, but also we have other peak that corresponds to the graphene that is bonded to oxygen. And this is very important in catalysis, because we want to have defects, we want to have oxygenated functions, and this indicates that we have some carbons that are bonded to defects. Also in this case, in the case of chitosan, is a nitrogen doped, because we can prepare not only graphene made of carbon, but also graphene doped with heteroatoms. And in this case, what happens is that the precursor, the polysaccharide, is a polysaccharide of glucosamine. So the natural compound already contains nitrogen, is glucosamine. When you pyrolyze, the 17% nitrogen content becomes reduced. But at the end, what you have is a graphene that contains about 7% nitrogen or lower, depending on the temperature of the pyrolysis. So here we have in XPS the nitrogen, and we have 3 populations of nitrogen, 2 major ones. This is the graphitic nitrogen, so just taking away a carbon and putting a nitrogen gives this signal, but also we have another nitrogen that is the pyridinic. So just in the border we have some nitrogens, and the borders there they are not fully saturated, and this is the pyridinic nitrogen. And this is again the electron microscopy images, so we can count how many layers we have in this sample, and you can also make by contrast and count here the separation between the layers, that is always 0.3, 0.34, and an expansion with high resolution shows that all the atoms are aligned, so we have something that is very well crystallized. Of course, when you have films, you can measure conductivity, and here is the setup that we are using to measure the conductivity. Here is the film, and here we measure the conductivity, and this is the type of cells that we prepare. And the conductivity of our graphene is about 100, 200 ohms squared. So this is not the limit. There are much better graphenes for conductivity than ours, but we should not forget that we want this graphene with defects for catalysis. So doped graphene we can dope with other heteroatoms, for instance, besides nitrogen, that is just prepared by pyrolyzing chitosan that contains carbon and nitrogen. We can also produce graphene doped with boron. In this case, the procedure consists in forming polysaccharide solution, and then we make the ester, because most of the polysaccharides they form inorganic esters. For instance, the reaction between boric acid and the polysaccharide form the borate. This is very well known in sugar chemistry. So we form here the ester, and then by pyrolysis what we obtain is a graphene that contains some boron. Depending on the conditions that you pyrolyze, the amount of boron can be higher or lower, and this depends on the pyrolysis temperature. And also we can prepare graphenes having 2 elements, boron and nitrogen. This is very important from the catalysis point of view, because boron will introduce acidity, nitrogen will introduce basicity. So considering the major reaction mechanism, acid-base is one of the major ones, and here we have a material that contains both acid and basic sites. And also redox sites, because redox can be quinone, hydroquinone, and these are the effects on graphene. So just we follow the work by Bielaski in 2010, showing that graphene oxide is a good catalyst without any metal for performing the aerobic oxidation. This is very important because they are using just oxygen to promote oxidation. Using oxygen alone, you have an alcohol, and at the end you produce benzaldehyde. But in this original paper from Bielaski, they were using graphene oxide in a very large amount. Typically, per weight was 50% weight of graphene oxide and 100% weight of the alcohol. So by using our doped graphenes, so we were able to reduce the amount of graphene that we were producing. Actually, we were working 1 weight percent, only 1 weight percent, while here was 50 weight percent. And in that way, we can oxidize benzylic positions. For instance, in this case, we obtain the alcohol and the ketone just using oxygen. And also, we are able to oxidize carbon-carbon double bonds of alkenes to form epoxides and aldehydes. And this is very interesting because when you perform the kinetics, when you follow the kinetics of the reaction, you observe that using this catalyst, this carbon catalyst, there is always an induction period. An induction period because the mechanism of this reaction is always a radical mechanism. So we need some time to generate some radicals, in this case about 3 hours. But what we notice is that as soon as benzaldehyde is formed, then the reaction starts and becomes accelerated. So we make an experiment in where we on purpose added benzaldehyde, because it's known that benzaldehyde in combination with oxygen can promote radical reactions. And by adding benzaldehyde at the beginning of the reaction, what we observed is that the induction period disappears. So really, we have other evidences that show that the role of graphene in these reactions with oxygen is just to generate the first radical. We have used this ability of graphene for oxidation also to perform the degradation of lignin. That is one reaction that is very important in biomass transformation, because lignin is the second most abundant constituent in biomass, and lignin is a very complex polymer that contains many different unions, and one union that is here, that is a 4-beta oxygen bridge, 4-beta oxygen bridge that has here in this model. So we were using this model, as a way to make the polymerization of lignin, and using just graphene, reduced graphene, what we observe is just very high conversion for the oxidation of this model. These are the products that we obtain. There are two colors, because one color corresponds to one ring, and these are the products that come from this ring, and the other color is the fragment that comes from the other ring, and we can follow the time conversion plot showing that the selectivity changes with the time, but at the end we can have very high selectivity for the formation of Y-alcohol. So this is a very interesting reaction, because for this process, lignin depolymerization, there is still not any catalyst in use. So the thing is that when you want to replace an industrial process that already contains a catalyst, this is very costly, because you have to change all the process. But if you start in one reaction in where still there is no industrial process, then you have higher chance to have a catalyst that can be implemented. So here the conversion is very high and the system works very well. Graphene as Fenton catalyst. This reaction is very important for water purification, for the decontamination of water. And this is one reaction that typically always have been reported using metals. The typical metal for this is iron, and iron in combination with hydrogen peroxide, iron becomes oxidized, and the key point of the Fenton reaction is that hydroxyl radicals are generated. Hydroxyl radicals, this species, is the most aggressive species that can be present in water. So in water there cannot be anything more aggressive, more reactive than hydroxyl radicals, and using hydrogen peroxide and iron 2, so then we generate this hydroxyl radical. The other thing is that then iron 3 becomes reduced to iron 2 also by hydrogen peroxide. So hydrogen peroxide is very nice because can oxidize and can reduce. And here what we are doing is oxidation, but also here you are using the reduction. So the combination of these two processes, at the end, what happens is that with two molecules of hydrogen peroxide, one molecule gives hydroxyl radical and the other molecule is decomposed to oxygen and performs the reduction of iron 3 to iron 2. If you go to the literature, all the examples have been reported with metals. So we are talking about metal-free catalysis. It's possible to develop a graphene that is able to do this reaction, and actually these are the temporal profiles of the reaction showing that really our graphene is very efficient for the Fenton chemistry. So this is reduced graphene oxide, and this is one graphene, and we are following two plots. One plot is phenol. That phenol is the IUPAC recommended molecular probe to test the Fenton. So to test the Fenton, if you go to IUPAC, IUPAC recommends this probe. So then what we observe is over the time, using reduced graphene oxide or our graphene, we can decompose phenol, and this is another graphene oxide in where the activity is lower. So there are some graphenes that they are very good, other graphenes they are not that good. It depends on what is the composition of the graphene. But one thing that is important is to compare this phenol with hydrogen consumption, and then you measure what is the slope of this plot and the slope of this plot, and you have to find that they are parallel. So this is very important because this means that hydrogen peroxide is only decomposed making this reaction. Is only decomposed making the Fenton. If you degrade one phenol, then you have to decompose two molecules of hydrogen peroxide. Actually, when you compare this scale and this scale, you will observe that we have the double. So one thing that always worries in using graphene as metal-free catalyst is there any impurity, any metal present there that is acting as catalyst, and we are confusing the small amount of metal and thinking that is the carbon. So we on purpose make some experiments in where we add different amounts of manganese on purpose to see what is the influence of the presence of manganese in this amount. And this is just the conclusion of this, in where we plot the reaction rate constant against the amount of manganese that we on purpose add. I have to notice that these samples of graphene have never touched manganese, have never touched any metal. But manganese is one of the typical metals that promote the Fenton. And maybe during the life, the insect or the shrimp has been in contact with some metal, so maybe chitosan contains some metal, or maybe the algae contains some metal. So this is the plot that summarizes what is the influence of the reaction rate constant with the amount of manganese, and what you observe is that yes, there is some influence, there is some increase, but if you extrapolate to the zero amount of manganese, something that probably is never possible to be done. But if you extrapolate this line, what you observe is that there is still a very significant activity of graphene without any metal. So basically, we cannot have a sample totally free of impurities. But we can study what is the influence of the impurity by making these plots and different concentration of manganese. Activation energy. One thing that is important in a very good Fenton catalyst is that the activation energy for phenol degradation and water hydrogen peroxide decomposition should be the same. And here is the conclusion. This is the activation energy for phenol decomposition and hydrogen peroxide, and it coincides. So this means that really this catalyst is very good for Fenton reaction in the absence of any metal. However, we have other graphene, for instance, graphene doped with nitrogen, that is not very good. And here, for instance, the reaction rate, the activation energy is much higher. But not only this, what happens is that for hydrogen decomposition, the activation energy is lower. So this means that this graphene is very good for the composition of hydrogen peroxide, but without leading to the degradation of phenol. So it decomposes hydrogen peroxide very fast, but it does not degrade phenol. While this other graphene is very good for both things. So it's a hallmark of the Fenton chemistry. Of course, we have direct evidences that graphene, in the absence of metal, generates hydroxyl radicals. And the best proof is this, is just to use a EPR trapping agent, and this reacts with hydroxyl radicals and obtains this EPR spectrum that contains structural information, showing that without any doubt, by measuring the coupling constants, what we have is the adduct of the probe with hydroxyl radical. This is the simulated spectrum in red, and the comparison of the simulated spectrum with the real one. As you can see, the simulation and the real one coincides very well. So really, we have evidence that graphene alone is able to generate hydroxyl radicals. One thing that I have not commented, and probably now is the moment, is that graphene has nothing special compared with other organic molecules. So really, carbocatalysis and organocatalysis, they are not so different. And here we have some other molecules, for instance, this one, that is also able to do Fenton chemistry in the absence of metal. And so with these probe molecules, we have shown that it's also possible to generate the Fenton reaction. So this leads us to the conclusion that the centers that we need in graphene to promote Fenton reactions are these, quinone and hydroquinone. Actually, in very old organic chemistry, it's known that quinone and hydroquinone is a redox pair, is a reversible redox pair that has a redox potential very similar to iron 2 and iron 3. So the redox potential of this pair and the redox potential of iron is very similar. So there is nothing new, except that we have a graphene that should contain oxygen functionalities and many defects, and for this reason is able to promote the reaction. So this is the mechanism. We have determined what is the efficiency of hydroxyl radical generation, and this efficiency changes during the course of the reaction, but the top is about 80% of the consumption of hydrogen peroxide, 80% is forming hydroxyl radicals. And also we have other indirect evidences, for instance, quenching with OH trapping agents like DMSO, and the reaction stops. This is without DMSO, the same reaction. In the presence of this hydroxyl radical quencher, the reaction stops. Productivity, notice this scale. This scale is 1 order of magnitude larger than before. So we can degrade a lot of phenol, and actually we have determined what is the turnover. The turnover number, considering that our sites are oxygenated functions, and the turnover is 4,500 for degradation of phenol. That is not very high compared to the state of the art. So the state of the art of metallic catalysts, the turnover is about 10,000 or so. So it's not the record, but we are very close to the catalytic activity of some metals. And probably our hope is just to design a specific graphene that contains the higher density of the sites and to increase the turnover. Graphenes can also be carbocatalysts for the oxidation of amines to nitriles. So this is one reaction going from here to this. It's a reaction that has industrial relevance. And what's happening in this case, we are not using oxygen. What we are using is hypochlorite as oxidizing agent, and it's very interesting because the first process that is going from the benzylamine to benzylamine, this does not require catalyst, but what requires catalyst is the overoxidation of the imine to the nitrile. So we have determined the reaction mechanism, and we have established that here is the rate determining step that requires the action of a catalyst, and in this case graphene oxide is a good catalyst for the process. In the case of aliphatic amines, the reaction works very well, particularly for long chain amines that are the most interesting ones from the industrial point of view, and in this case the yield can be 100% for the formation of the nitriles. Again, what are the active sites? Do we need just an ideal graphene? And the active sites are the peracids and perlactones that are formed by using this reagent. So the first thing is that this is the graphene in the absence of the reagent, but if we have a hypochlorite, then some bands appear, and these bands that appear have been identified as peracids. Again, coming back to organic chemistry, what is special in the case of graphene? And the answer maybe is nothing, because it was known that if you have an acid and you have an oxidant, so then you form the peracid. And it was known that the peracid was able to do this chemistry, oxidations. So really, these are the active sites, and what we need is just a graphene that contains some oxygenated functional groups. Graphenes can also be catalysts for hydrogenation in the absence of any metal. And this case is one very interesting case, because this section is also oil and petrochemicals, because just one of the effluents of cracking of oil, contains a mixture in where ethylene is in a very large excess. But ethylene has an impurity, a small amount of ethylene. And this causes a lot of problems because it polymerizes and it have risk of explosions and everything. So what the point is how to purify this stream just by removing ethylene. And one of the possibilities will be just the selective hydrogenation of acetylene in the presence of very large excess of ethylene. And just using graphene, so what we observe is that we can hydrogenate ethylene 81% and only promoting the hydrogenation of a very small amount of ethylene. So this is a very important target, because in that way, if we are able to hydrogenate only this compound to this compound, so then there is no point on purification because we have already purified. Of course, graphene can also promote the oxidation, the hydrogenation, in liquid phase. This gas phase. In liquid phase, we have alkenes like cyclohexene, cyclooctene, and this is a time conversion plot showing that we are able to hydrogenate different alkenes in the liquid phase. And this is the reaction mechanism that we think. So what we need is an acid-base pair, and we activate hydrogen in that way, and we have determined what is the role of impurity in this case. So I have 2 more minutes. So also in this case, we studied the influence of manganese, and it's clear that there is no influence. We make poisoning with base to show that we need acids. We make poisoning with acids to show that we need a base, and the reaction mechanism has been proved. So then with this doped graphene, we have prepared by pyrolysis of alginate. This is the phosphate ester of the alginate, and we have boron phosphorus doped graphene. This is the evidence that graphene contains some phosphorus incorporated into the layer. And then graphene becomes from conductor to semiconductor, and we can use this phosphorus doped graphene to do photochemical reactions. This is the phosphorus NMR, showing that we have in the graphene 2 different types of phosphorus, one that is similar to the phosphine, and another that is similar to phosphine oxide. These are the images of the phosphorus doped graphene, and we have used this for hydrogen generation from water using solar light. And this is the hydrogen generation. This is the first use, and this is the reuse of the material. And this is the micromoles per gram and per hour that we are able to generate. And of course, if we put some platinum, then the activity increases, and then what we have is 300 micromoles of hydrogen per gram. So this is the summary, is that most of the catalysis of the last century was based on metals, noble and critical metals, but sustainability requires to change to a new generation of catalysts that can be renewable, and carbocatalysis can be in that way to develop carbons that can have active sites, and graphenes offer many opportunities because this is just the limit of carbon, and graphene can replace metal catalyst. So the point is,
no, please. Yes.
Thank you very much. In case of hydrogen production from graphene, you said by putting metal on top of it,
yes,
you can have 300 micromole per
yes,
hour, right?
yes,
So is it without sacrificial agent or with sacrificial agent?
with sacrificial agent. We have submitted for publication a paper in where we use just water, pure water. This is overall water splitting. So we publish step by step first.
Did you measure oxygen as well?
Eh?
Did you measure oxygen or?
Yes. We measure oxygen. We have the stoichiometric amount between oxygen and hydrogen. Yes, sure. Yes.
I just want to ask you a question about normally graphene is a small powdery material. So if you were to use as a catalyst, the problem is to separate the product from the what you call the starting material. That is going to be the problem. So any possibility of putting on the support, but so far I think it's quite difficult.
Yes. I have mentioned that there are two possibilities. One is to use in suspension as in a liquid, but also we can put a film, so we can cover the reactor. Actually, some of the reactions that we are doing now, they are on films. So you have a substrate that can be flat, but can also be round, and you cover with the graphene, and then you use as catalyst. So you don't need to separate.
Okay, we thank you, Professor Gracia, about his talk, and we thank him very, very much about this. The next speaker with Professor Muhammad Mukhtar. He is from King Abdulaziz University, and at chemistry department he will talk about layered double hydroxides as efficient alternative to homogeneous catalysts in the synthesis of fine chemicals. Please start, Doctor. You have 20 minutes. Is it 20 minutes? Yes.
Okay. Thank you, Mr. Chairman. I would like to thank the organizing committee for inviting me as an oral speaker for this talk. So the title of my talk today is Layered Double Hydroxide as Efficient Alternative to Homogeneous Catalysts in the Synthesis of Fine Chemicals. Shortly, for our guests that are coming, Jeddah is named the pride of the Red Sea, and our university is founded 50 years before. It's an university. Okay. So again, okay. Thank you. So the conference essentially is established because of the 50 years passing of the King Abdulaziz University, and this is so we are celebrating this day the 50 years of foundation of our university here. So just jumping to the talk, I would like to introduce just a background of the layered double hydroxide. Layered double hydroxide, they are hugely important class of layered materials. Originally discovered by Professor Kempf, and it's named according to the Deutsche, which is called Doppelschichtenstruktur, which is double layered hydroxide. This is originally coming from magnesium hydroxide brucite structure, where the divalent cation is substituted by trivalent cation in the cationic sheet. Accordingly, we have huge positively charged in these layers. So it's compensated by water molecules and some anions like carbonates. Originally, once carbonates is coming, this name is changed into hydrotalcite because of the carbonates inside. They have some hydrogen bonds between the cations and the interlayered anions as well. And this smart material have unique characteristics will explain in these characteristics, but one of the most important things is the location of the cations in the cationic sheet itself, which is tetrahedral, octahedral sites, and what happened if you substitute the divalent by trivalent one, what's exactly the new location of these cations, what its effect on its properties, as well as what's the effect of the interlayer anions in between these galleries. So the general formula for this material is written here, and as I said before, they have many applications. We'll explain it in details. Again, the unique property of the layered double hydroxides coming from the position of the cations, you can see here, for example, the magnesium hydroxide itself could be 3 magnesium cations surrounding the wedge. Otherwise, we have double substituted by the magnesium cation in the octahedral site by divalent cations, which is by trivalent cation aluminum, or there will be changes in the structure upon thermal treatment of the material. So, the well-known property of this material is what's called the we studied the effect of thermal treatment on this material in order to find a question or an answer to the what's called the memory effect of this material. The layered material could be thermally decomposed between 70 to 200 degrees centigrade. It's just dehydroxylation of the material, so we can have keeping the structure of the cations itself without collapsing of the structure. In this stage, which is intermediate phase, we can return back again by what's called rehydration process, where the structure is completely kept and returned back again to its original position. If we decarboxylate the material by increasing the temperature from 300 to 580 degrees centigrade, we could completely remove the carbon dioxide and water molecules from the interlayer, so we can have the collapse of the structure. Smart mixed metal oxide is formed in that case, and if we hydrate again the material, we'll never have the original structure, but we'll have another new material which is called mixenrite, where the hydroxyl ions only substituted in the layers, while the carbon dioxide is completely removed. To complete the story of this material, this is just to make a right definition to every stage of this material, but for every stage there is a nice application in the fine chemical, as we'll see. So again, for the acid layer double hydroxide itself and the mixed double oxides, as well as the hydrated one, there are different applications. For the acid the heterogeneous solid base catalysts for wide variety of organic transformations, I'll explain later. And mixed metal oxides, because of the increasing the surface area due to the collapse of due to the decomposition, removal of carbon dioxide hydroxyl groups, we increase the surface areas of porosity, as well as we create a Lewis phase sites, so it will have another applications, or rehydrate the material again by passing water vapor in the gas phase or liquid phase, so we could introduce another terminal hydroxyl groups which have another catalytic activity. So this is just a scheme to explain to you how much there is an application. For example, the layer double hydroxide, once it's collapsed in the metal oxide, we have usually prepared the metal oxide via hydrothalcite route. What's the advantage of this material? Once you synthesize the material at the beginning in the form of layer double hydroxide carbonate, then they calcine this material to have the metal oxide. You have unique property for the metal oxide you prepared now, because you're introducing the more Lewis acids, more Lewis basic sites are there, and find many applications, especially if you substitute the aluminum by nickel or cobalt or copper, whatever. So you can originally prepare different metal oxides via this route. If you reduce the metals in the layers itself, after calcination, you have supported metal oxide directly on the layer that you already formed. So you don't need to prepare the support and then do impregnation of the material, then reduce the material itself. So you can self-synthesize one and only one material, then you control it later on. And this gives an advantage for the application of such material. Again, hydration, rehydration of the material introduce some terminal hydroxyl groups which have more basic pronunciated basic sites, or you can do uniform distribution. So you can have electrophoto-catalysts, which is used in the application for catalysis as well. Or we can completely remove the interlayer anions and replace it by DNA, polymer, whatever, and have another applications for the intercalated layer double hydroxide. Or as our group with the collaboration of UCL London and Imperial College supported the layer double hydroxide on graphene oxide and tested this smart material for the CO2 absorption, and this found very good application as an absorption. So graphene oxide improves the absorption capacity of the layer double hydroxide itself. Or you can do delamination for the material, and according to delamination you can have gold nanoparticles on the ultra thin film, and which has a very good application performance is oxidation of glucose. Again, the calcination of the acid side material, you can create a nice mesoporous with large surface area of the material. Our previous studies, in order to find or try to find an answer to what's happening in situ calcination of the material, what's the phase transformation, what could happen is it possible to leave the octahedral site in the cationic sheet, or will keep the cationic sheet in the octahedral site, or what's the effect on the catalysis? So did in situ XRD measurements as well as neutron diffraction measurements. And at the conclusion from such nice work that already published in the Chemistry of Materials, Materials Chemistry, and Clay Science, we could say aluminum trivalent ions that were promoted to tetrahedrally coordinated lattice sites. And this is very important because you now move the cation from the octahedral site to the tetrahedral site, and this will affect the catalytic activity, or explain to us why this catalyst is very active in certain processes. For the fine chemicals itself, a nice mix between catalyst and organic senses we have to synthesize these fine chemicals. Usually people using classical homogeneous catalysis, and this is of course have many problems. So replacing by solid base catalysis is one of the target of the people who are interested for the environment and the green chemistry, because solid base catalysts give you cleaner catalytic alternative, non-corrosive, as well as good reusable regeneration many times. So have many advantages rather than the homogeneous one. If we compare between the solid acid catalysis, solid acid base catalysis, solid base catalysis, this is the percentage of application of such catalysts in the literature. We can say that our solid base catalyst is just 8%, but I would say, is it really layer double hydroxides only basic catalyst, or they have some acidic properties? We'll see during our application. So the applications of layer double hydroxide in the sense of fine chemicals, the acid synthesized material is found to be better than the mixed metal oxide X layer double hydroxide, and did 100% conversion at 150 degrees centigrade for the methyl tributane to all into acetone and alkyne. Applications in the fine chemicals also aldehyde condensation of cetraluzastone in order to have the beta ion with its wide applications. Beta ion with 80 to 80% was prepared using sodium hydroxide. 100% conversion was attained by layer double hydroxide, so you can replace the soluble basis by the regenerated layer double hydroxide, as well as you have 100% conversion using this smart material. For the mixed metal oxides, the X-hydrotal site, which have more Lewis basic sites, they found a nice applications better than the alkaline exchanged Y zeolites, as well as the acid HY zeolites for the formation of flavanone. According to some principles of the green chemistry, prevention, less hazardous chemicals, designing safer chemicals, safer solvents, and catalysis, and following up what these principles, mixing the layer double hydroxide, which is environmentally benign metal hydroxide, in the sense of fine chemicals, our research group, we started using ultrasonic irradiation for the layer double hydroxide, which is zinc, aluminum hydrotalcite, comparing this catalyst with the usual classical catalyst, basic alumina, KF basic alumina, silica. We found that in comparison for the conventional method, we have 90% yield. The time in hours was 1 hour, but using ultrasound irradiation, the time is reduced up to 10, and the percent yield is increased much more. So this means combining layer double hydroxide, which is environmentally benign, as well as the tool itself, which is irradiation with ultrasonic. This gives promotion to the obtaining of such important material for the fine chemicals. Another nice piece of art, which is a magnesium hydrotalcite as efficient catalyst for Michael or as a Michael addition. This paper is cited many times in literature because in this paper exactly we would say it's not 100% basic material because of the presence of aluminum center, which is aluminum trivalent. You have some Lewis acetate, so it can say acid basic catalyst, at least under the reaction conditions for the formation of azomical process. Another piece of art was using magnesium hydroxide itself as efficient catalyst for the microwave assisted regioselective 1,3 dipolar cycle addition reaction. If we compare between the catalyst itself using microwave conditions and conventional one, we can find also shifted from 75 yield % in case of conventional method, we have the microwave addition increases the yield and reduces the time of course. So now mixing again between another tool for the green senses of the organic materials instead of the hazards, classical methods of the organic people using long time hazards materials and lower yields. This means layer double hydroxide itself and metal oxides derived from such material could have an impact for changing completely the route. The approach is quite clear, is to substitute the classical methods, organic one, by the layer double hydroxide, and in addition of another techniques, we can go to more to the green and safer methods and methodologies of the preparation of the fine chemicals. In addition to that, the nice work, which is a CC coupling, which is important, like Suzuki coupling, Ullmann coupling, and homogeneous CC coupling by aryl formation, using in the literature using complex copper material, and the copper should remove the iodide, forming cuprous iodide, cupric iodide at the end of the story. But replacing this catalyst, usually this catalyst need base, need complex, which is never to be regenerated again. So what about if we introduce the copper itself in the cationic sheet, and we have already the basic properties of the material? So we can have the copper in the cationic sheet, and we have the basic properties of the material itself. So we can use it at one and only one catalyst for the senses of the for the cis coupling. We tried this work, and we found that by replacing isomorphal substitution of the magnesium divalent from the cationic sheet by copper, we succeed to have the best catalyst for the senses of the for the CC coupling under microwave irradiation. Nowadays, our recent work, which is current research now, according to the beginning of the using microwave assisted reaction in order senses, what about if we use layer double hydroxide, cobalt, copper, and so on, without even using the microwave assisted reaction for the senses of the CCRIL? And this work, we supported the copper layer double hydroxide on graphene oxide and cobalt aluminum double hydroxide on the graphene oxide, and comparing between different cations. Originally, cobalt copper substitutes magnesium, isomorphal substitution of the magnesium in the cationic sheets without any change, without any impurities. This means just to remove magnesium, adding cobalt or copper in this sheet, but they have two different properties. Copper itself, without supporting graphene oxide, found higher % yield at the fresh catalyst. For the fresh catalyst, we could find that the copper is better than copper supported graphene oxide, better than cobalt unsupported, better than cobalt supported. But what happened if we do the reaction, reuse the reaction many times? So after filtration, dissolving, and so on, for the regeneration of the catalyst, you can find graphene oxide catalyst, supported catalyst, better yield after 5 or 6 times regeneration. And this is originally coming from the unique properties introduced by graphene oxide as support for the layered double hydroxide, where first of all we have change in the porosity of the material. This is unsupported one, this supported one. So mesoporous, creation of the mesoporosity, this is one of the points. Second point is the onset start of the reduction. This means we have from the TBR measurements, it reduces, enhance the reduction of the layered double hydroxide earlier, and this means once you enhance it earlier, you have both a change in the surface area increases, it's 100% more than the unsupported one. Second one, you increase the reducibility, so you have reducibility as well as large surface area, and this is why graphene oxide after certain times of the regeneration provide constancy. I came already to the summary of the work. So from the summary you can say layered double oxide itself have many beneficial features such as low cost, selectivity, catalytic properties, and wide range of the preparation modification methods. The whole promise of providing sought after environmentally friendly technologies for the 21st century, replacement of currently used homogeneous alkaline bases for the sense of fine chemicals by solid catalyst can result in the catalyst reuse and waste stream reduction. The challenge for the future applications of layered double hydroxide in the sense of fine chemicals in terms of green protocol processes were presented. At the end of the story, I have to do acknowledgement for our partners, Chemische Reaktionstechnik by Erlangen Nuremberg for the Institute XRD measurements, London Center of Nanotechnology, Imperial College, UCL London for the diffraction, for the neutron diffraction measurements, Professor Suleiman Bassam, the head of the Surface Chemistry Studies Group and Chemistry Department, Dr. Nisreen Saeed is the partner for the Organic Sciences guys, my students, all my students, and Dr. Tamer and Dr. Rao, who are helping in the all the published papers that presented today. And thank you very much for your kind attention.
If there is any questions.
Yeah, thank you for this amusing lectures, and just small questions. After using the catalyst many times, is the structures or layered structure of hydrotalcite is changed?
This is a very good question. Usually, it depends on the reaction conditions. If you have liquid, usually in the liquid phase organic reactions, we tested the catalyst after 5 times regeneration, the work that published for the microwave assisted one. We found some contaminations, even if you make careful washing of the material, you have some intercalated organic materials in the material itself. And this is why it's much better either to use the layered double hydroxide in the gas phase reaction or to support it another support and try to solve this problem. It means, because also the possibility is not only the memory effect is causing the reformation of the structure again, but we believe that there are some kind of dissolution and recrystallization again. And this is a problem that facing this material in the application industry, because it could be dissolved, they recrystallized again, changing some of the structure. There is some change, but in comparison to the others, still have an advantage than the others for the application.
Is there any questions from the ladies upstairs? Thank you, Dr. Mohammed.
Oh,
thank you very much.
Thank you very much.
The next speaker with Professor Muhammad Kamil from India, and he will talk about the preparation and the study of boronic F127 monolayers at the air-water interface. Welcome, Dr. Muhammad.
Yeah.
Dr. Muhammad. Dr. Muhammad. You have 20 minutes.
Yeah, thank you so much. Just S. Full size. No, no, size. Take, okay. This one. First of all, I would like to thank the session chairman and also the organizers of this conference who had given me the opportunity to present my work over here. I belong to India. I am working as professor in the Department of Petroleum Studies, Aligarh Muslim University, Aligarh, that is very close to Delhi. My work is basically the preparation and study of pluronic monolayers at air-water interface. The outline of my presentation includes about the introduction of the monolayers, the Langmuir-Bloget technique which is used for the characterization of the monolayers, the technique for the preparation of monolayers, as well as the characterization part which has been done based on the measurement of surface pressure, and then the surface pressure area isotherm, the study regarding the pluronic film, and then the conclusions as well as the future work. The Langmuir film of pluronic has been prepared on pure water as a surface. The film has been organized by the repeated compression and expansion. The properties of the monolayer of the non-ionic copolymer pluronic at air-water interface and the effect of the anionic surfactant sodium rhodesyl sulfate that was characterized by using the Langmuir-Truff method. The surface pressure versus mean molecular area isotherms in the water phase, they were measured in the absence and presence of SDS molecules. The isotherms of the monolayer showed the characteristics of the pancake to brush transition upon compression of the monolayer. The effect of increasing loading of the polymer was also studied. Further, the effect of repeated compression and expansion cycle, that is basically the hysteresis curve, has been investigated to know about the stability of the film. Static elasticity of the monolayer, that also gives information about the molecular arrangement, phase structure, as well as phase transition. Now, as all of you are aware that polymers are basically widely used in the nanotechnology applications so as to produce materials such as hybrid organic inorganic materials and also the porous membranes. Such applications require a thin polymer film from which the various physical properties needed for the desired nanotechnological applications. The properties of the polymer may be controlled two-dimensionally by forming a polymer monolayer at an air-water interface. The compression of the barriers can change the packing density within the monolayer and consequently also the rheological state. A polymer monolayer may also be easily transferred to a solid substrate by using the polymer Bloget technique. These possibilities give the potential for the use of a polymer monolayer in technological applications. The cross-linking basically causes polymers to have a higher mechanical strength and often results in its swelling ability to be better controlled due to defined swelling behavior. Such properties are very important as in the drug delivery system.
Surfactants have been used to physically or chemically cross-link polymer gels, which are used in the drug delivery system. However, the introduction of the ionic surfactant into a non-ionic polymer has been reported to cause the polymer to cross-link at low to intermediate surfactant concentration, and also to break up the polymer at high concentrations. The cross-link basically occurs because of the hydrophobic interactions, and it is known that the surfactant acts to cross-link a bulk polymer through the complex formation of the polymer and the surfactant. The effect of the surfactant on the physical properties of a polymer chain in a polymer monolayer at the air-liquid interface is still not very well understood. Pluronic, which is a tri-block copolymer whose repeat unit consists of two terminal polyethylene PO oxide molecule and a central propylene oxide PO block, which was chosen as the polymer. The central polypropylene oxide groups can be expected to act as a hydrophobic anchor at the air-water interface for the hydrophilic PEO blocks, which lead to the formation of an insoluble pluronic monolayer at the air-water interface. The sodium diadecyl sulfate SDS was chosen as the surfactant, and its tail is sufficiently hydrophobic to allow binding to the hydrophobic groups of the polymer, but not hydrophobic enough to allow the formation of an insoluble monolayer at the air-water interface. This polymer surfactant system therefore enabled us to study the effect of the surfactant on the polymer monolayer. The large size of the pluronic molecule offered a large degree of conformational freedom, which was imagined to give a plenty of possibilities of surfactant binding to the polymer. We had used a Langmuir film balance to control the lateral packing of the molecules in the monolayer, and thus the conformations available for the anchored polymer. Its phase behavior was studied via the surface pressure versus the area per molecule isotherm at a constant temperature. Temperature control was important as the onset of gelling of a bulk pluronic aqueous system has been reported to occur at 30 degrees centigrade. The study of surfactant monolayer is necessary to know about the molecular orientation and also the stability of the monolayer at the air-liquid interface. It basically serves as a model system to examine the condensed matter phenomena and also used to model biological membranes to produce liposomes for application in drug delivery system. Monolayer adsorption is used in flotation, stability of the food, and stabilization of emulsions. Surfactants, as I said, that basically these are the compounds that lower the surface tension of a liquid. The interfacial tension between two liquids are that between a liquid and solid. Generally, the molecules of a surfactant consist of hydrophilic and hydrophobic part, and the surfactant diffuses in water and adsorbs at the interfaces between air and water at the interface between oil and water. These are the compounds of the amphiphile, hydrocarbon chain, and the hydrophilic part. The various type of surfactants has been classified as anionic, bearing the negative charge, cationic, having the positive charge, non-ionic surfactant, amphoteric, Gemini surfactants, and biosurfactants. Surface tension is basically the measurement of the cohesive energy present at the interface. All of the molecules of the liquid attract each other. This diagram shows the various forces acting on the liquid molecules near and at the interface. The amphiphilic nature of the surfactant dictates the orientation of the molecules at the interface in such a way that the polar head group is immersed in the water and that the long hydrocarbon chain is pointing towards the air or toward the gas or oil. So a thin organic film can be deposited on a solid substrate by various techniques. These include thermal evaporation, sputtering, electrodeposition, molecular beam epitaxy, adsorption from solution, Langmuir-Blogy technique, and self-assembly. This Langmuir-Blogy technique is the promising method for fabricating ordered ultra thin films on the solid substrates at the molecular level by transferring monolayers from the water surface. These LB films provide information on the arrangement and orientation of molecule as well as transition and conformational changes. These are useful for studying the basic properties of functionalized and amphiphilic dye block at the interface. This precise control of monolayer thickness can be accomplished. Homogeneous deposition of the monolayer over large areas can be ensured, and also the possibility to make multi-layer structures with varying layer composition. This is the diagram of the Langmuir balance which was used. The various parts of the Langmuir mini trough having the balance trough which is filled with clean surface, that is water, movable barriers and Wilmy plate for the measurement of surface tension. This is the spontaneous spreading of the liquid of surfactant molecules by the syringe. Few steps regarding the preparation of monolayers, that is the preparation of lipid solution, assembling of the trough and barriers, the Wilmy plate, filling of the trough with ultra pure deionized water, expansion of the barriers to the maximum. Then a precision syringe is filled with the desired volume of the prepared solution of monolayer, material dissolved in the volatile organic solvent. The syringe is gently pushed to produce a droplet at the end of the needle and then touch the surface with the tip of the needle. Approximately 20-minute time is required for the solvent to evaporate, after which the measurement can be started. This is the diagram showing the surface pressure, Wilmy plate which is partially immersed in the surface, and surface pressure which has been measured in order to characterize. This can be defined as the difference between the surface tension of the pure liquid surface, that is water, minus the surface tension of the liquid covered with the monolayer. So when the Wilmy plate is partially immersed in the surface, various forces act on this plate, and these forces are measured and they are acting on this upward buoyancy force due to the displaced water, gravity force which is acting downward, and the surface tension force, and we can make the force balance which has given by this equation, and we can measure the change in the force for a stationary plate between a clean surface and the same surface with the monolayer present. This is the schematic example of the surface pressure area isotherm exhibiting the variety of phases which can occur, gaseous followed by the liquid expanded LE, then we have the LC liquid condensed, and finally the solid phase. And this diagram shows also that this is the typical for the lipid monolayers, schematic representation of lipid packaging at the monolayer interface. So as the pressure increases, we go from gaseous to the collapse state. The phase behavior of the monolayer is mainly determined by the physical and chemical properties of the amphiphile, the surface temperature and the composition. Monolayer states depend on the length of the hydrocarbon chain length and the magnitude of other cohesive and repulsive forces existing between head groups. An increase in the chain length increases the interaction between molecules, condensing the surface pressure area isotherm. Another parameter is the directional modulus. The elasticity of the Langmuir monolayer is one of the important parameter of its serological property. By measuring the elasticity of monolayer, one would be able to understand the state of monolayer and also its changes, for example, molecular arrangement, phase structure, phase transition and relaxation behavior, and we can calculate it by the slope of the surface area and concentration of the isotherms. The various work which has been reported either on water or on some other surface, mainly the Langmuir trough has been used, and most of the work which has been reported in the literature, they are without the surfactant, and in fact in my work basically we had used the anionic surfactant and we had compared that. So the objective of our is to determine both the surface properties of the polymer monolayer and the effect of the surfactant to the polymer monolayer, effect of increasing loading of polymer and hysteresis cycle and static elasticity of the polymer. As I have told you about the polyuronic tri-block copolymer, and this is the protocol regarding the formation of it. The various materials which has been used for the preparation of monolayer. So a monolayer of polyuronic was prepared by spreading the draw wires on the pure water surface from a 12.4 molar solution in the chloroform using the syringe. Surface pressure area of the molecule isotherm for the polymer monolayer, they were measured at 25 degrees centigrade, and we had used the Langmuir Miniturf system for this. The surface pressure we can use for the preparation of the pi A isotherm. The film is compressed towards the center of the trough, and the surface pressure versus mean molecular area was recorded by this, where the various terms have their usual significance. Now this is the comparison between the surface pressure area isotherm with and without the surfactant. So the blue one, that is the curve A, basically shows the variation of the surface pressure mean molecular area for pluronic polymer, and this green, that is B curve, shows about the curve with the surfactant, that is the anionic surfactant SDS. Now we can observe something here, that the surfactant was used as the 10⁻⁻⁴ mole of the SDS to the water, and also the curve without water. This corresponds to the concentration of 29 micromolar in the surface. This is well below the concentration, that is the CMC, critical micelle concentration of the SDS in water, which has been reported as 8 millimolar. This indicates or ensures the absence of micelles in the surface. The surface pressure increased as the pure monolayer of the polymer was compressed. A change in the slope, that is pseudo plateau, is obtained as polymer goes through pancake to brush transition. With pluronic, the maximum surface pressure that was reached was around 16.7 millinewton per meter, and with the addition of 10⁻⁵ mole of SDS, the maximum surface pressure increases to 24.28. The effect of adding surfactant to the surface was to shift the isotherm to larger molecular areas. The addition of surfactant also decreased the stiffness of the monolayer. This increased flexibility can be explained either by the more fluid nature of the SDS molecules in comparison to the polymer molecules, and the electrostatic repulsion between the surfactant groups in the monolayer are binding between the hydrophobic PO groups and the hydrophobic tails of the surfactant molecules. Similar work has been reported in the literature, and they have reported the surface pressure values as 15.5, whereas in my work we are getting 16.7, which is quite comparable to that one reported in the literature. This is a diagram showing the pancake to brush transition for dilute spreading solution as well as for concentrated solution. This diagram shows the effect of the surface pressure versus the number of cycles plot for 12.6 kilodalton molecular weights of pluronic, and the surface was water. When the spread film is subjected to repeated compression expansion sequence, we got the highest pressure that increases after reaching the surface pressure of 17.4. It decreases after each cycle, and the figure shows that cycle as a function of surface pressure as the number of cycles. The figure shows the effect of increasing the loading of polymer on the stability, 7.5 microgram to 15 microgram, and the maximum surface pressure was observed as 20.91. Now you see that when we increase the loading from the dilute solution as to prevent clustering and forming a more coherent film, the resulting isotherm has been shown, and moreover the isotherm shows slow rise and then it shows the steep rise. We got the high loading of pluronic, we obtained the maximum surface pressure of 20.91, though the maximum surface pressure is increasing, but the isotherm is shifting towards lower mean molecular area. This is the regarding hysteresis, and you see that a possible cause for the hysteresis in the film during the first compression is that compression forces some of the film into the aqueous surface, because the isotherm of pluronic is miscible with bulk water in all proportions at room temperature. The amount of the loss of polymer in terms of reduction in the mean molecular area is due to the dissolution into the surface and difficult to come back on the surface as pluronic is miscible with water. Just I am finishing it. This is regarding the dilatation modulus, and the elasticity of the monolayer on compression and expansion having almost the similar curve that reflects the film becomes cohesive and elastic in nature, and the value has been reported which is also quite comparable to that which is in the literature. These are the results which have been obtained for the film. The important conclusions is that on adding the surfactant, surface pressure increases as the introduction of ionic surfactant into a non-ionic polymer causes the polymer to cross-link at low to intermediate surfactant concentration and break up the polymer molecule at high concentration, and also by increasing the loading of the polymer, surface pressure increases. Elasticity curve for compression having similar trend as found by other workers. These are the references, and thank you very much for your patience hearing.
Thank you, Professor Kamel. Is there any questions, please? For ladies, any questions? Thank you very much, Professor Kamel. The next speaker was Dr. Muhammad Hamdi Saad from Saudi Arabia, King Khalid University. Huh?
Yes, correct.
Yeah, correct. Khalid University. He will talk about the novel bifunctions catalyst with the high impact.
Thanks, Mr. Chairman. Good afternoon, everyone, and welcome in my presentation. Well, my presentation today entitled Novel Bifunctional Catalyst with High Impact. My name is Muhammad Hamdi, and I'm working as Associate Professor at King Khalid University. Well, what is a bifunctional catalyst? So in general, if we check UBAC definition, the bifunctional catalyst, this is a catalytic substance which possesses two different catalytic active sites, and it can perform actually two different catalytic functions at the same time. Well, if you start to think about engineering the catalyst, if you'd like to design a catalyst, you might face some challenges. Something like, what is the nature of your active sites, as I just mentioned, that we need to have two different functional groups. So what are the nature of this active group or active sites? Is it isolated or nanoparticles or bulky crystals? What kind of support you are going to use, or you will use it without any kind of support? What is the synthesis mechanism? Is it something easy to synthesize? Is it one-step procedure, or it is a difficult and complicated synthesis procedure, or what? And finally, cost of your material. It's quite important to have a cost-effective substance. Expensive chemicals should be avoided if possible, and so on. Well, this is the support that I used, which is called TUD1. It seems like, okay, this should be a high-resolution three-dimensional TIM image for TUD1 structure. Well, TUD1 is a siliceous material, so it's made totally out of silica. It's three-dimensional mesoporous structure. It's simple one-step synthesis procedure. It's quite easy to control the synthesis, highly reproducible, and the most important feature in this material is that the texture properties of this material can be tuned during your synthesis. So you can really control your surface area, your pore volume, and your pore diameter. And it's cost effective. We don't have here to add any kind of copolymer or surfactant or whatever. If you compare between TUD1 and the other mesoporous materials, the most famous one, MCM 41 and SBA 15, well, in so many publications so far, TUD1 has benchmarked these two materials as a support. The synthesis of the bifunctional catalyst, as I just said, that you can really control your synthesis. So you add your template to your silica source. You will add two different metal sources, whatever they are, with a precise ratio, and you will adjust the pH by tertiary ethyl ammonium hydroxide. by adding some water, and the overall synthesis mixture is going to form gel by aging for 24 hours and then drying for another 24 hours. Finally, hydrothermal treatment step, and in the end, if you calcine your material at 600, you will get 1 gram of your catalyst out of 5.5 gram of your substrates. Well, actually, as I said, there is so many advantages by using this technique to prepare your bifunctional catalyst. It's one-step synthesis procedure, so you can really add 2 different functional groups with 2 different ratios in the same time supported on your catalyst. It's all in one-step synthesis. It's solvent-free and surfactant-free busway. It's cost-effective. You don't have to add any surfactant or copolymer, and so on. Well, I will give now 4 different examples for the bifunctional catalyst. Let's start with the first one. If you have isolated titanium and isolated hexavalent chromium ions supported on the TUD1, and actually this is a very old trick. People published a lot about shifting the absorption spectra of isolated titanium to work as a photocatalyst in the visible light region. And for the first time, actually, we applied the degradation of 5 different gases in the same time. So we applied methane, ethane, ethylene, propane, propylene, 25 ppm per each, to totally degrade these 5 gases to carbon dioxide and water. So that was our aim of study, and we expected during the design of our catalyst, we expected the role of chromium-6 to absorb photons in visible light region, and it can be excited itself or send the energetic photon to titanium-4 to perform the photocatalytic job. Well, actually, if chromium itself can work as a photocatalyst, so why you just don't use it itself without adding any titanium? It's quite simple. If you increased in the loading chromium percent than 1%, you will start to get some kind of nanoparticles of chromium oxide, chromium-3 oxide. So, and this one has been reported many times that it is not photocatalytic active. So you really have to keep this one over 1% and do this trick just to enhance the photocatalytic activity of this material. Well, synthesis, so this is titanium chromium TD1. This is the material that we prepared, and we characterized by many characterization technique, XRD, UV vis, Raman spectroscopy, TEM, and the nitrogen photosorption. And one of the, I will show you only 2 of the interesting characterization techniques that we used. So this is the Kubelka-Mank function of titanium-1. So it can absorb light till 300. If you add 1% chromium to this material, you really can shift the absorption spectra towards the visible light region. So in principle, you really prepared what you aimed to. But is it really chromium-6? Why it is not chromium-3? We confirmed this by Raman spectroscopy by 2 different Raman machines. And this one has been performed actually in Lehigh University in the States. So this is the catalytic performance of this material. Here, this is titanium, 1 or 1% titanium alone supported on silica matrix. You see almost there is no degradation at all of your gases. If you add now your chromium alone, so methane is quite stable. You will start to get very small degradation in ethane, in ethylene. In ethane, it's stable. In propylene, yeah, you can find some degradation. And in propane, you can also get something like 15 to 20% degradation. However, if you combine these 2 together, so you have your titanium and your chromium, so this is the result that you will get. Methane is quite actually a stubborn molecule to be degraded, but you can fully degrade 3 of the 5 gases within 2 hours. So almost 75 ppm of your gases has been totally gone within a couple of hours. And this actually was reported last year in JAX. So that was the first example, and as I said, this is the very traditional example to shift the absorption spectra of titanium to the visible light region. Well, let's going to the traditional catalytic examples, and here we have a system consists of titanium 3 isolated active sites, plus we have also some iron oxide as a nanoparticles embedded in the TUD mesoporous structure. We aim to use this system in the benzylation of benzene-Friedel-Crafts type reaction to form biphenyl methane in different temperatures, and our expectations before we start, that is the acid sites in isolated iron 3 will activate benzyl chloride, so one of the reactant, and in the presence of nanoparticles iron oxide, this metallic oxide center will activate the benzene ring, and I will show you in a minute what is the effect of activating the two substrates instead of activating only one substrate. Well, this is the material that we prepared, iron TUD1 with different catalytic ratio. The characterization we characterized also by so many techniques, and for the first time actually we could see the iron oxide nanoparticles embedded in the TUD1 by high resolution TEM. It's in a range of 5 to 6 nanometer. And by mass power, we confirm the presence of this iron oxide plus the isolated iron 3 ion. Okay, let's go into the catalytic activity. Well, we compared the materials that we prepared with siliceous TUD1 without any iron and with iron oxide, and we also prepared some iron doped mesoporous material like MCM41, HMS, and MFI, and so on. And actually, we got a very unique catalytic activity, which is this one. So 10% of iron doped in TUD1, and the reaction has been finished totally within less than 1.5 minutes in a state of 4 hours with only 1% of iron. So moving from 1% of iron, only one kind of active sites, you end this reaction within 4 hours, but with 2 active sites, this reaction has been done within 60 seconds. Well, this actually result was so unique, so we needed to confirm this result. So we performed actually in situ FTIR study for this kind of reaction, and this is the benzyl chloride. Actually, this spectra has been recorded every 30 seconds for this material, 1% of iron in TUD1. This is the substrate. It takes 4 hours to be consumed, and this is the product. It takes also 4 hours to be formed, but in the presence of 2 different active sites, this is what you expect to get. So here, this is the reactant at 0 time, after 30 seconds, after 60 seconds, after 1 minute, it's totally disappeared. This is the product, no product at 0 time, after 30 seconds, after 30 seconds. So this is the product, and the reaction has been totally done within 60 seconds. Well, this one of the my best examples actually to show the difference between using 1 active sites and 2 active sites. Recently, and this starting from here, this work has been performed at King Khalid University. So we needed actually to design another catalyst, contain 2 different active sites, metallic center, and we need also to have some acidity in our catalyst to convert the methyl isobutyl ketone into 2-methyl propanol directly. Normally, this kind of reaction actually has been performed in 2 different steps. You need first a metallic center to hydrogenate methyl isobutyl ketone, and then you need your acid sites to perform this kind of hydrolysis to form 2-methyl propanol. And actually, this in this reaction, we could perform it in 1 step by designing this catalyst. our expectations for the two different active sites. Platinum is a metallic center which activates the hydrogenation step, and the acidic sites generated by incorporation aluminum 3 in the framework of silica will, or we expected that it will be activate the hydrolysis step. Well, this is the material that we prepared. We prepared aluminum, platinum, TuD1 with different ratios. We characterized the material with the available characterization techniques at King Khalid University. And well, this is a high resolution term of this material, and you can clearly see the highly distributed particles of platinum in the silica matrix, and the XRD, which confirms the presence of platinum as well. You don't see here any peaks for aluminum as an indication for the total incorporation of aluminum in the silica matrix to generate the acidity. And this is the catalytic activity that we get, and actually this is the first time that this reaction has been performed in liquid phase reaction. And by using platinum aluminum TuD1, you will get 13% conversion and 99% of selectivity towards 2-methyl propanol, the desired product. We replaced platinum with ruthenium, with silver, with palladium. Ruthenium give also considerable activity, but not as platinum one, and this work has been submitted recently to Journal of Catalysis. The last example that I am going to show you in a very classical reaction, the selective oxidation of cyclohexane to cyclohexanone and cyclohexanol. Here we needed also to design a catalyst contain two different active sites, cobalt-2 and different nano particles of metal oxides to selectively oxidize cyclohexane to cyclohexanone and cyclohexanol. Well, for if you check in the literature, so the mechanism, one of the mechanisms that has been proposed for this reaction, including the oxidation of cyclohexane to cyclohexyl hydroperoxide, which is going to be decomposed to cyclohexanone and cyclohexanol, and then over-oxidation reaction occurs to form different oxygenated products. But here actually we aim to design a catalyst like this, so the cobalt site will work to oxidize cyclohexane to cyclohexyl hydroperoxide, and the metal oxide center should be facilitate the hydrolysis of cyclohexyl hydroperoxide to form the aldehyde and ketones. We prepared actually different materials. The base was cobalt supported on silica, and including some zinc oxide nanoparticles, manganese oxide nanoparticles, titanium oxide, vanadium oxide, chromium oxide, copper oxide, and so on. We characterized also this material as much as we have in our department. And actually this is the results that we could obtain so far. We have, of course, some kind also of unique and strange results, something like chromium and cobalt. We got 42% conversion with selectivity almost 90%, but chromium is not stable in the framework and it's leaching, and this is most probably due to a homogeneous reaction, not heterogeneous. But we have also here some kind of very stable system like cobalt manganese, like cobalt copper. We could record some leaching of copper, but cobalt is quite stable, and we have something like 17.5% conversion. Also, yes, this one, cobalt and strontium, we have 15% conversion, 80% selectivity, and so on. And actually, this table was reproduced from the master thesis of my student Amal El-Shehri. And I'm going to conclude my presentation. Bifunctional catalyst, actually, if you really study your reaction in a good way, you can design a very good bifunctional catalyst. And the advantage of using TuD1 as a support, it's one-step synthesis, it's cost-effective, it's tunable texture properties, and it's active in so many different applications. In the end, I would like to acknowledge my partner in different universities. In Twente University, Khidumul, Rizvana, Amrullah, and Hindra. Hindra was one of my master students. Rizvana my first PhD student in Delft University, Ulf and Patricia, from Texas University, Ramanasan Anand, from Bochum University, Jennifer and Anna, King Khalid University, Abdullah Hanash, Murad Isa. Murad was also one of my master students. He will defend his thesis after 2 weeks from now. Amal El-Shehri, one of my master students as well. And I would like to thank all of you for your kind attention. If you have any question, I would be more than happy to answer it. Thank you.
Thank you very much, Doctor. Yes.
Just I would thank you for this very what's called very
Inspiring?
no very interesting lectures, because I am interesting also, you know, with
Yes,
these
I know.
materials. Yeah. The first questions is by definitions. I'm just a small confused. Bifunctional catalyst is the catalyst that two functions, or the catalyst that make two different reactions?
Well, actually, if you check in the EUBAC definition, it has been called that this is a catalyst which contains two different functional groups and can perform two different catalytic function at the same time. So it's one material, contain two different functional groups.
But your work is you have two functions,
Yes.
but make only one reaction.
Yes, two different catalytic group. It doesn't mean that you have two different reactions.
Yeah.
It could be two different steps.
Yeah. Is the other questions, the loading the metal on TUD1, is this is done during the preparations or
Yes,
after preparation?
it's all one-step synthesis procedure.
it's
You
in
mix
progression.
all your material in a liquid state to get a gel, and then just go to a calcination. You will get your material. That's it.
Okay, thank you.
Thank you, Dr. Muhammad. Thank you very much.
Thank you.
Yes, thank you.